Now let's move on to confidence intervals for proportions. When we want to estimate a population proportion, we should be using the binomial distribution. However, when the sample sizes are big enough, it's a lot more convenient to use the normal distribution. And the central limit theorem allows us to do that when the sample sizes are big enough. So, in order for the sample size to be big enough to approximate the binomial distribution with the normal distribution, we need our sample size times the probability of success and the sample size times the probability of failure. Both of those two products need to be equal to or greater than 5. So a quick review. The binomial distribution is a discrete probability distribution that represents the number of successes in a fixed number of independent trials. N is the number of trials. Each trial only has 2 possible outcomes, success or failure. The probability of success is P, which should remain constant. And the probability of failure is the complement of P, and we label that as Q. Our variable X is the number of successes, and the trials must be independent. Our notation for the binomial distribution is X with the tilde, then the capital B, and then inside we have the sample size, comma, and then the probability of success. The mean of a binomial distribution is labeled as mu, and we find that by taking n times p. And the standard deviation is the square root of n times p times q. So quick refresher. When we use the normal distribution to approximate the binomial distribution, this is what it looks like. So our binomial distribution is the bar chart, and then the smooth curve over top of that is your normal distribution. So when we approximate the binomial distribution with the normal distribution, we would change our notation to X with the tilde and then the N, and then we would use our mean for the binomial distribution and the standard deviation for the binomial distribution. That would be the square root of n times p times q. Let's look at the first example. In a study to evaluate the effectiveness of a flu vaccine, a random sample of 800 individuals was observed after receiving the flu shot. Out of these 800 individuals, 600 did not contract the flu during the observation period. You are asked to calculate a 99% confidence interval for the true proportion of people who do not get the flu after receiving the vaccine, based on the sample data. This confidence interval will help you assess how effective the flu vaccine might be in preventing flu cases. So, we're given the sample size of 800. We're given the number of successes, that's 600. 600 people did not contract the flu. So let's write down this information. We definitely know we're dealing with a proportion. So we're going to use a z estimate for a proportion. Our sample size is 800. Our number of successes, X is the number of successes, that's our variable, that's 600. And we want our confidence level to be 0.99. Now, we also need the probability of success, and the probability of failure. That was not directly given to us, but we can quickly figure it out. If I want to find the proportion or the probability of success, since we have 600 successes out of 800, that would be a probability of 0.75. We would take 600 divided by 800. Now the probability of failure is the complement of that, so that would be 0.25. So even though they didn't directly give us that information, we had enough to figure it out. This was 600 out of 800, and then the complement is what's left over. That would be the 200 out of 800. So let's make sure that we choose the correct estimation method. We're doing a z-estimate for a proportion. That's this one right here. So we're using the normal distribution to estimate a binomial distribution. And we can do that. I forgot to mention this when we were looking at the problem, but remember we need to check to make sure the sample size is big enough. And to do that, we need to take our sample size times the probability of success. So that would be 800 times 0.75, and that gives us 600, which is certainly bigger than 5. Then we got to do the same thing for our probability of failure. We would need to take our sample size, 800, times the probability of failure, which is 0.25. That gives us 200, which is definitely bigger than 5. So this is something that we can use the normal distribution for to approximate this situation. So I chose the correct method. We're doing a 99% confidence interval, so that's already in there from our last question, which is nice. The number of successes, we were told that there were 600 successes, and the sample size was 800. And so now when we look down here, we get our lower limit, which is 0.7106, and our upper limit, which is 0.7894. And our error, what we're adding and subtracting to our point estimate, which is our probability of success from our sample, that's our P. We're going to add and subtract the error. We get 0.0394 for the error, and we'll check that by hand here in just a moment. But before we can check that by hand, we need to find our z-critical. Why are we bouncing back to z? We just talked about t, but remember when we're using the normal distribution, we use z-scores. And since we're approximating this binomial distribution, with the normal distribution, we need to use z-critical, not t. So I'm going to go back to my distribution. I'm going to make sure I'm on the normal distribution. And make sure that since this is standardized, we want to use 0 and 1 for our mean and standard deviation. Since we have a 99% confidence interval, that means there's 1% left over in total for the wings, and then we have to split that between the two wings. So each wing is going to have 0.5%. So checking the left wing first, I'm going to put in 0.005 for 0.5% in decimal form, and we get negative, when we round it to two places, we'll get negative 2.58. Let's check the right wing. I have 0.005. We get the same value but positive. When we round it to two places, we have 2.58. Now, if we want to double check it, we can use the in-between brackets. So I want to go between negative 2.57583 and positive 2.57583. And when we do that, look, we have a probability in between that our area is 0.99. So we know we've got the correct values, although we're going to round it when we write it down. So we're going to list it as 2.58. Okay, so I've written everything down that we got from GeoGebra. I wrote down our confidence interval, our z-critical, and the error that GeoGebra came up with where it was rounded to 4 places. So let's try calculating this by hand. So let's find the error. So for proportion, the error is z-critical times the square root of p times q over n. That n is under the square root as well. So I'm going to plug in all of our information. We have 2.58 times the square root of 0.75 times 0.25, all divided by 800. When we do that, I get 0.039498. Pretty darn close to what GeoGebra had. It's slightly off, probably because we rounded the critical value to 2 places. All right, so if we take our point estimate, remember for proportions, the point estimate is the sample proportion for success. So that is our p-hat. So that's our 0.75. So we're going to take our point estimate, which is 0.75. We're going to add the error, which is 0.039498. When we add it, we get an upper bound of 0.789498. That is really close to what we got on GeoGebra. A little bit off because of rounding. The lower is when we take our point estimate and subtract. So we're going to take 0.75 and subtract the error, which is 0.039498. That's going to give us 0.710502. Again, really close. So you can see how rounding an intermediate step can throw off your answer, which is why it's very important to follow the rounding directions in the homework to make sure that we're all getting the same answers consistently. So our conclusion is that we are 99% confident that the true proportion of those that did not contract the flu is between 0.7106 and 0.7894. Notice that I use proportion, not mean, because we're estimating the population proportion in this case. All right, let's do another one, example 6. In a random sample of 850 office workers across major tech companies, there were 527 that indicated they prefer a hybrid work model, which means combining remote and in-office work, and that was over returning to full-time office work. We're going to construct a 90% confidence interval for the proportion of tech workers who prefer a hybrid work arrangement. So we have a sample size of 850. We have the number of successes is 527. We're going to call a success here the people that prefer a hybrid work model because that's what we're trying to track. So that's what we're considering a success. Okay, so we have a confidence level that's 0.90. And now if we want a probability of success from the sample, we're going to take 527 out of 850. That gives us 0.62. So that means our probability of failure is going to be 1 minus 0.62, which is going to be 0.38. Okay, now I want you guys to practice this one on your own. Pause the video, try using GeoGebra and entering your values to see if you can get the correct confidence interval. When you enter all the values in GeoGebra, you should get a confidence interval with a lower limit of 0.5926 and an upper limit of 0.6474. So our conclusion would state we are 90% confident that the true proportion of workers that prefer the hybrid model falls between 0.5926 and 0.6474.